Have you ever stopped to think about how your phone call stays private or what keeps your Wi-Fi connection secure? Well, a lot of that magic comes from something called a stream cipher. And today, in this explainer, we're going to pull back the curtain on these tiny but incredibly powerful engines of encryption that protect our data one single bit at a time. So here's our roadmap. First, we'll get our heads around the basic idea of encrypting bit by bit. Then we'll go looking for the secret sauce, the part that actually makes it all secure. After that, we'll check out a perfect but totally impossible kind of cipher, and then finally, we'll see how the pros build strong, practical ciphers that we use in the real world every day.
Right, let's dive right in. What is a stream cipher, really? At its core, how does it actually scramble up our data?
Okay, so think of it like this. You've got two main kinds of ciphers. Block ciphers, which are super common for things on the internet, are kind of like packing boxes. They grab big chunks of data, a whole block, and encrypt it all in one go. But stream ciphers, they're more like a super fast assembly line. They handle each individual bit, one by one, as it comes flying down the pipe. This makes them really, really fast and efficient, which is exactly why they're perfect for things like your phone. Now, the engine that powers this entire thing is an operation that's actually surprisingly simple. It's called XOR. The best way to think about it is like a little light switch for every single bit of your data. You've got your data bit, and you've got a secret key bit. If that key bit is a 1, it flips your data bit from a 0 to a 1 or a 1 to a 0. If the key bit is a 0, it just leaves it alone. But here's the real magic. It's perfectly reversible. And you can see that right here in this table. Just look at that second row. Your original data, your plain text, is a 0. It gets combined with a key bit, which is a 1, and the result, your cipher text, is a 1. Now, to get your original data back, you do the exact same thing. You take that encrypted 1, you hit it with the same key bit, and boom, you're right back to your original 0. It's simple, it's elegant, and it's incredibly effective. Okay, so this brings us to the most important part of this whole system. It's that sequence of 1s and 0s that we're using to flip all the switches. We call that the keystream. And I want you to really let this sink in because it's the most important point. The XOR operation itself, that's not a secret. It's just basic math. The entire security of this whole setup, literally everything, hinges on that key stream. If that stream is predictable in any way, your encryption is completely broken. It has to be secret, it has to look random, and it has to be totally unpredictable. So the big question is, how do we generate this magical, unpredictable key stream? Well, we use something called a random number generator, or an RNG. Its only job is to spit out a sequence of bits that looks, for all intents and purposes, completely random. But as you're about to see, not all randomness is created equal.
You really have two main flavors of these things. On one hand, you have true random number generators. These actually get their randomness from the physical world, from tiny, unpredictable things like the thermal noise in a computer chip or the microscopic jitter in a system clock. You can never reproduce their output. Then you have pseudo-random number generators. These are just algorithms. You give them a starting point called a seed, and they use math to generate a sequence. Which means, if you have the algorithm and you have the seed, you can create the exact same sequence every single time.
But here's the thing. For encryption, your average pseudo-random generator isn't nearly good enough. We need something special, something much, much stronger. A cryptographically secure one. And here's the critical difference. With a CSPRNG, even if an attacker could see millions and millions of bits pouring out of this thing, they still wouldn't have any better than a 50-50 chance of guessing what the very next bit is going to be. That's the kind of hardcore unpredictability you need for a secure stream cipher.
You know, this all leads to a really interesting thought experiment. If the security of our cipher depends entirely on the randomness of the key stream, what would happen if we used a perfectly random key stream? We're talking about the absolute holy grail of cryptography here. It's called unconditional security. And this isn't just about being hard to break. This means a cipher is so perfect that even if an attacker had a supercomputer the size of a galaxy and all the time in the universe to run it, they still couldn't crack the code. It is fundamentally, mathematically impossible to break. And believe it or not, a cipher with this level of perfect security actually exists. It's called the one-time pad. The rules are dead simple. You use a truly, perfectly random key stream, and you never, ever reuse a single bit of it. If you do that, you have achieved perfect, unconditional security.
But, and this is a massive catch, your key has to be the exact same length as your message. So you want to encrypt a 1 gigabyte movie file? No problem. You just need a 1 gigabyte key made of pure random data. And that is why the perfect cipher is almost completely impractical in the real world. Okay, so if perfect security is off the table, what's the practical answer? How do we take a short, manageable key, say 128 bits, something we can actually handle, and stretch it out into a super long, unpredictable key stream that acts a lot like that perfect one-time pad? Well, one of the classic answers is a clever little piece of hardware called a linear feedback shift register, or an LFSR. The best way to picture it is like a little pinball machine for bits. You'll load it up with an initial state, your key, and with every tick of the clock, the bits all shift one spot over, and a feedback loop uses that same XOR operation to figure out what new bit to launch back into the start of the machine. It's a really simple device that can take a short key and spin it into a very, very long sequence that looks pretty random. And you can see it right here. Let's say we start with the state 100. On the next clock tick, everything shifts, a new bit gets calculated and fed back in, and now our state is 010. And this just keeps repeating, cycling through a sequence of states that, on the surface, seems random, but is actually marching along a perfectly predictable path defined by its internal wiring.
And that's the big problem. See the L in LFSR? It stands for linear, and that linearity is its fatal flaw. Because it follows a simple, predictable mathematical rule, an attacker only needs to see a small chunk of the output. With that, they can basically solve a set of equations, figure out the internal wiring of the machine, and predict every single bit that will ever come out of it forever. So on its own, an LFSR is totally insecure. So now we have this weird situation. We've got this simple, fast little component, the LFSR, that can produce long sequences with good properties, but it's also fundamentally broken and insecure all by itself. So how do we actually use it to build something strong?
In this question right here, how do you build something strong out of weak components, is really at the absolute heart of modern cryptographic design. The solution is just brilliant.
You just combine them. Instead of relying on one predictable stream, you take multiple LFSRs and run them all at the same time. Then, and this is the secret ingredient, you take their outputs and you feed them into a complex, nonlinear mixing function. That nonlinearity is what creates the magic. It basically smashes together all the simple, predictable patterns from the individual parts and creates a final key stream that is a chaotic, unpredictable mess. You've literally built a strong, secure system out of fundamentally weak, broken pieces.
Phew, we have covered a ton of ground. So let's take a step back and boil this all down to the key things you should really walk away with.
So here's the bottom line. Stream ciphers are these super fast, super efficient little engines that are perfect for securing things like our mobile phones. And while perfect, absolutely unbreakable encryption does exist in theory, it's just not practical for the real world. So the real genius of modern cryptography, and maybe the biggest lesson for today, is this. It's the art of taking simple, predictable, even insecure parts and combining them in a very specific, nonlinear way to create something that is incredibly complex, unpredictable, and ultimately very strong. And that leaves us with one final thought. We've seen that amazing security can be built by creating complexity from simple parts. But as our world gets filled with more and more data streams from our cars, our homes, our medical devices, the challenge is always evolving. It's about finding that perfect, elegant balance, simple enough to be fast and efficient for all these new devices, but complex enough to keep our secrets safe from ever smarter attacks.